Good morning. A little bit of science today. Since we started sending things out into space, we've had quite a bit of payback, very practical payback in the whole field of communications. We've also had a lot of science going on, and it's going on constantly, and we just tend to hear some of the news at times, but mostly it's quiet. In one of the old Star Trek episodes, the crew come across an entity that is called VGER, and by the end of the episode it turns out that VGER was actually Voyager 1, and it had certain qualities that we don't expect out of a mechanical object. But the Voyager 1 and Voyager 2 go back a long way, launched in 1977. We got a lot of information from them, and just recently it's been confirmed that Voyager 1 has definitely broken a milestone. It has left what we call the solar system, which is simply the area where the solar flares have the greatest influence, in contrast to the area outside the solar system, where you're seeing the results of the emanations of many stars over many, many years. And the indication for this is using something called a densimeter. You try to find out how the concentration of electrons, and unfortunately the one functioning in Voyager 1 stopped functioning about 20 years ago, so we had a hard time figuring this out. By fortuitous means, it was determined that yes, Voyager 1 has definitely left the solar system. When Voyager 2 goes out, the densimeter is functioning, and we'll know very precisely when it leaves. Way out is something called the Oort clouds, which is a source presumably of the comets that come into the solar system, but that'll take a long time to get to. And we'll have some more information, or someone else will have some more information at that time. So that's a biggie. There's a lot else that's been going on. We have, of course, the tremendous accomplishments of the Hubble telescope, which really opened up the universe to us, and it's you would have to spend a book time to go through everything that they've done. We've had the Kepler, which has indicated the probable existence of planets around other stars, and we're anticipating the Webb telescope, which is a monstrously large telescope at a monstrously large budget of about $8 billion. This is an infrared telescope. When you go out a great distance in space, then you run into the fact of the age of the universe, and the fact that the expansion of the universe, and the farther away you go in space and time, the faster it draws away from us. This changes wavelengths, and we get what's called a redshift. At a certain point, it's no longer a redshift. It's shifted totally outside the visual spectrum, and so the Webb telescope is an infrared telescope, huge, and it's going to tell us an awful lot of what we want to know about the early universe. Now, there are two studies that I'm interested in, and they've related to the space stations. The first one was in two sections, and it relates to dark matter. Dark matter is sort of the poor man's road to really advanced scientific investigation. With conventional studies like in CERN, where you had these zillions of people coming together with this huge construction where you took charged particles and accelerated them to near the speed of light and had them bang into each other and produce results. You had very precisely controlled beams, and you could really mathematically determine what happened. And of course, the big payoff for the CERN was the demonstration of the Higgs particle and Higgs boson. And this particle was sort of a break-off from the Higgs field, which explains mass. This is really an important thing. It was a triumph, quietly, though we also got a lot of other exact measurements. And physics is all about exact measurements. You just want to be able to bounce one discovery off another. But the CERN collaboration was immensely successful. The area I'm interested in is one which looks for dark matter, and it utilizes the fact that that in supersymmetry, what we think of the dark matter, every particle is its own antiparticle. So what we're dealing with is a statistical collection of the production of positrons in the orbiting space stations. And this is statistical. The big problem is that while the collision of the smallest particle in the supersymmetry in dark matter with itself produces an excess of positrons, these are also produced by pulsars. So we have a statistical question here. The difference is the pulsars produce it at a different energy pattern than the ones that come from the dark matter. So what we're doing is collecting the statistical count on the energy pattern of positrons that are picked up on the space station, and we're just trying to draw conclusions. So we've gotten preliminary results after about 3 years of data, and they definitely point to the existence of dark matter related to the smallest particle of supersymmetry. And this is tremendous, except that while a physician, I would say, oh, it's proven, I go by very lax statistical standards, would accept this. No, physicists don't accept that. And it'll probably take like another 18, 20 years to get enough data to say, yes, this definitely shows that the LSP, the least supersymmetric particle, exists, and we have confirmed the nature of dark matter, and it is related to supersymmetry. And we will be very happy about this, but it's going to be a long time. Physicists take a long time making up their mind. See you next time.